This is a search tree. So search tree formality. What does that mean? Formality. Formal definition. Equation or mathematical. Okay. Define that the tree structure is like that. Each node. Okay. Each node has a PK, 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 P, K, P. What does that mean? P. Pointer. And K means keyword. What does that mean? For example, in each node, I have a pointer for one child. Okay? Then one key. Another pointer for another child. So 10. And 20. So that means less than 1. For example, your search data is 0. Can you find the 0 here? But 0 is less than 1. Then you can find the 0 here. What about the 9? 9 is bigger than 1, less than 10. You can find that one in this children node, child node. So that is P, K, P, K. P is what? Children node pointer. K is the keyword. Actually, each keyword has what? Data pointer. Eventually, we are going to access the data file. Okay? Eventually. So, what is, for example, I write search SSN is equal to 1. 1 is here. When you find this one, that has the data pointer. Then you can find the data. So, that is described here. Okay? Everybody can understand that one? Okay? So, this is a simple example of the search tree. P is equal to 3. What does that mean? P is equal to 3. P means 3 looks like the 3 level. Actually, the degree of the each index node. How many children pointer? Okay, how many children? Maximum? When I was young, not young, when I was a kid, like 10, 15, probably elementary school. I'm from South Korea. South Korea is a very high population density. Really very high. Still high, but it was very high when I was a kid. So government would like to control the birth rate. So each family can have the only 2. It's not forcefully, but does suggest like the maximum 2. I heard a similar policy in China. So one child for family to control. Actually, that is the big mistake. Why? Consider the Japan. Japan still I think the last 2 decades, 20 years is the economic crisis. Do you know why? There are several reasons. One of them is because most of the young people, they don't want to have any child. So population graph, probably you learned the population graph in your sociology class, like this one. What is this? This is the age 0 to 100, and this is the population for each age. So we have huge number of population in old age, over 55, 60. And this is the young people. What's the problem? Who is the main consumer of your product? Generally, the young generation. But if you have the very narrow and small, such a generation, we do not have a consumer, then economy will not be running. That is one of the examples you can find in Japan. And right now, China is okay in the point of view. But if we sometimes later, if it's the society is getting average old, that will be the problem. Usually, the young people also support the old. Using what? Tax, pension. So, for example, I'm using the social security account, so I save the money for the future as a pension account. Then that money is in the bank account only? No. It's now used for older people. Okay? In my account balance is there. So when I'm 55, 60, I can use that money. But right now, where is my money? It's currently used for the elderly. Okay? So, but if this is narrow, we cannot support it. That is a big problem. But why? So anyway, this is the number of the pointer. How many index key entry can you have in this case? Index key is in between, right? How many? Two. Always p minus 1 number of index key entry. How many children pointer? 3. That is the degree, a tree of order. Search tree, the tree order. Tree order means, in this case, the number of children pointer. And number of index key entry. That is p minus 1. Don't forget, each index key entry is not just a number. Always, it has what? Another pointer. It's a pointer of what? Data 5. So 5, the address is blah, 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 blah. And the 10, and the James, and address is blah, blah. 5 is a point, is blah. Okay? And 10, for the 12. 12 point, data block. Each key entry has the data block. So don't forget, each one has the data block. Okay? Then, this is a search tree. Then we can search the data easily. In many of the applications, even not the database system, we use such a the search tree. Benefit? It's easy to search, easy to implement. Problem? I will give the extra point, really. If you can find any problem from here. When you are using the search tree for your indexing structure in your DBMS system.
What if you take one side? What if you take one side? Like,
I will give extra point for you. That is the correct answer.
No point to the parent. No.
And he's correct.
Yeah.
So, anyone who can explain his answer? Why don't you answer louder?
I said, it's a point to keep the rect on one side.
It's a skewed tree. Why skewed tree is problem? If you can answer that, that will be perfect.
It's similar to like binary. It's similar to binary tree or linear search because you have to keep going.
Binaries?
No,
tree?
you remember how you said like, it feels like first it's good, but then you go all the way right here, it's bad. So if it's skewed, first is good, but if you go all the way right here, it's
Yeah.
bad.
Same idea. Can you explain in terms of the database concept? Yes.
You cannot determine like for the each level for the to search the particular data how much depth
Yes.
it should go.
In other words, for example, I try to extend the tree structure. So we have another tree, another children, another children. So we have here, so let's say 15 over here. How many are you to access including the data block? How many are you to find the lead? 5. How many are you?
2, 3, 4, 5, 6, 7.
1, 2. That's it,
Yeah.
right? What about the 3?
3.
3.
1, 2, 3. What about the 12?
4.
1, 2, 3, 4. What about 15?
7.
2, 3, 4, 5, 6, 7. Any problem? Think about the MTA. Sometimes 1 hour, sometimes 2 hours, sometimes 10 hours. Do you want to take that MTA when you make the plan for your travel? Probably not. That's not reliable. The reason why we select the MTA train is it's always 1 hour or 1 hour 15 minutes. 1 hour 15 minutes. It's guaranteed almost 99%. Okay? What about the this index? Sometimes 1, sometimes 2, sometimes 7. So in terms of query optimizer cannot guarantee the speed of using this one. Okay? It doesn't matter how long it takes. Okay, sometimes fast, sometimes slow, but it's not reliable. So we need reliable. Always the same time arrival, okay, same time duration. That is better. Even though the MTA takes the 2 hours, we like to use that instead of driving I-95. If we are lucky, it takes 30 minutes if we drive to 200 miles per hour, but sometimes it's 10 hours if you stop, okay, because of traffic or the accident. So that's the same reason in database. So we don't want to use the search tree because of the query optimizer doesn't like this huge data. We cannot find actually the average cost. Instead, how can we address the problem? The last question, if you can answer this one, is really perfect. How can we address that problem? Split. This is a skewed tree. We can make balanced tree, not binary. So we can make the balanced tree. Okay. B3 index, B or B plus 3 is a multi-level index. It's a balanced. Balanced means always is the leaf node is the same degree, same level. Okay, not skewed one unlike this. Okay, that is B3 index, B plus 3 index. So when you see the B3 or B plus 3, B does not indicate binary. It's a balanced. Okay. For example, this is the example. It's a balance. All leaf node has 1 level, 2 level, 1 level, 2 level, 1 level, 2 level. So problem is how can we make the balanced tree? How can we make the tree structure, general search tree structure? It is top-down approach. It's go from the top to bottom. Because of that, some of the branch is growing. The solution, bottom-up approach. We start from always children. Okay? So how can we make that is the B3 index. So B3 index is, so we are going to use this one is a node structure. This is a one node. Okay? In this case, the order, okay? Order P means 1, 2, 3, 4, Q number of children. It's the same as the search tree. So order P, the order is Q. Then how many index key entry? Q minus 1, because in between 2, 3, 4. It's the same thing as the search tree. However, we are not going to create the search tree top to bottom. Instead, we are going to start from the bottom, then going up. Then let the leaf node will not be changed. Will not be skewed. Always going up. Then to do that, we need to use two operations. One is, I think he already answered whether one he remember. When we make the bottom to up, growing up, how to make this tree grow up? We need to first, if node is a full. Full means what? All index key entry is occupied. We cannot insert any additional keyword, any additional index key value. In case of full, we need to split. So how can? So this one will be 2 node simply. Then the data, this one goes to the left hand side, this one goes to the right hand side. So you have the space. At that time, this is a split. Another operation is after we split, we should know how can we access this one. Growing up patterns, create the patterns. So we can add 1 and 3, point to this, point to this. This is called promotion. The split and promotion. There are 2 operations in this, the binary at the B2 index, the balanced tree index. One is in case of full of index key entry, split, cut in half. Okay? Then next operation is promote. Promote means create patterns. Okay? That's simple. Right? Any question? Let's take a look at the example, then you can understand easily. So, for example, first, I think that we have the sample of the data. No? Let's see whether there is the sample data. Oh, here. 8, 5, 8, 5, 1, 7, 3, 12, 9, 6. So I simplify the problem. 8 means actually record is 8, is a key, and there are more data like the lead, address, and major CS, and so on. But I simplify only the index key entry 8. Okay? So 8 represent one record, but index only. So index value, index value, index value. Okay. Then always you should know what is the order. Okay. Q value. In this case, Q order is 3. 3 means how many children can you have? 3. Okay. So how do we know? 1, 2, 3. This is the index children pointer. Children pointer, children pointer, children pointer. That is Q. How many index key entry? 2. Q minus 1. Always Q minus 1, that is 2. So K1. But actually K1 has what? Data pointer. K2 data pointer. This is the node structure used in B3 index. Okay, then redirect insert. First, no data. 8 is inserted. We can create node structure. So 8 is inserted. That's it. So this is done. Next, 5 is inserted. So in one block, it's not a big problem to sort the data. We can sort 5 and 8. So 5 and 8. Problem is when 1 is inserted. What time is it now? What? How many minutes? 2 minutes? I think the 2 minutes is 4 minutes.
Yeah.
So it's enough. So 1 is inserted. Is there any space? No space. So we need to split into 2. How can we split? We need to order 1, 5, 8, then find the middle value. Which one is the middle value? 5. Then reassign, split into 2. We can have another exactly the same thing. Then left hand side going to left. 1. Right hand side going to right. Middle value will be promoted. We do not have the patterns, so create pattern. Okay, 5 goes to here. That's it? Not yet. You need to create children point. That's it. That's up to the 1. How does it go up? Bottom to up. Always to level. Next, 7. 7 is bigger than 5. Can I put the 7 over here? Always try to find the bottom leaf node. Okay? Always. So 7 is here. Do you have a space? Yes. We have one space, so 7 and 8. 7 is done. Next, 3. 3 is less than 5. Can I use this one? No, always find the bottom. So 1, 3. Next, 12. 12 is bigger than 5, goes to here. Can I insert the 12 over here?
No.
No, always, even though you have a space, find the leaf node. So 12 is here. Do we have a space? It's a full. In case of full, flip. So 7, 8, 12. And 7, 8, 12. Flip. Okay. Then, which one is the middle value? 8. Left hand side? Left. Right hand side? Right. And middle value? Promoted. Do I need to create?
No.
No. This time we can use this one. 8. Okay? Then check the children. Correct? Less than 5. Bigger than 5. Less than 8. Okay? Bigger than 8. Goes to here. That's it. Up to 12. What about 9? 9 is bigger than 8. So goes to here. We have space. So order 9, 12. 6. Bigger than 5, less than 8, goes to here. Yes, we have space. That's it. This is the B3 index. Simple. One more thing. 0 is inserted.
So it must be the second level.
So 0 is less than 5, supposed to be here. So full. 0, 1, 2. Which one is the middle value? 1. So we need to split into 2. Left hand side, 0. Right hand side, 3. 1 should be promoted. So 1. Do we have space? We can do the same thing in case of full. 1, 5, 8. This one is the middle value. Split. So left hand side, 1. Right hand side, 5, promoting. That's it. It's a growing top to bottom. Always how many level? 1, 2, 3, 1, 2, 3, 1, 2, 3. Check. Children point. Bigger than, less than 5, bigger than 1 goes to here. Be careful. Bigger than 5, okay, goes to here, goes to here. That's it. That's how B3 index is working. I will have the quiz next class. Okay, for this. This is the side. Then there is one problem. I said B3 index is balanced. Always provide the same level of the index data structure. Is it really true? For example, how we have the data file over here, so each one has the data pointer like this. Each one, even though I do not mention like this. What about 3? How many I/O do you need to find the data record 3?
4.
1, 2, 3, 4. What about 6? 2, 3, 4. What about 9? What about 5?
2.
What about 1?
3.
It's almost balanced, but not fully balanced. It has the upper bound, but it's still sometimes 1, sometimes 2, sometimes 3. Okay? Still, purely optimizer does not like such a the different level of the data. Okay? How can you address that problem? So that is the B plus 3 index. So it's a fully balanced tree. How we will discuss the next class. But idea is, why don't you put down all index key entry to the leaf node. This node has only separate, okay, classifier. That's the idea. How can we do that? We will see the next class. Any question? I know, I understand. I have been teaching the database. Even though it looks like easy to understand, please practice by yourself. Okay? So why don't you try it from the example in the textbook and this one, and try to draw the diagram. Also focusing on such a data structure. Then this B plus tree currently used in most of 99% of the commercial relational database management system. Then when you are doing the database project, sometimes if your administrator said your index is too high level, if you do not understand indexing structure, you don't understand what is the level, why it causes a problem. Right? So we will see how we can create the B plus tree. One more, last thing. This time, because this is the 2, the Q minus 1 index key entry is the 1, 2, 1, 2, so we can find easily the middle value. 1, 2, 3, middle value is this one. What if this is a 4, which means full, after full, we have this. What is the middle value? In case of the even average, no, we cannot use the average. So this time, it depends on the DBMS, or it depends on the developer. It's not critical, but in our example, in our class, in our textbook, we are going to use cardinal half and this one as the middle value. This is the agreement. So rarely, once in a year, there is always 1 or 2 students who select this one as a middle value. Then when I grade, it's totally different. So please select this value, cardinal half and left. There's no rule. But as long as you have a consistency, it's okay. But in my class, in our class, we will use the cardinal half and this one as the middle value. Please. Okay? If you are asking why, no. Just is between you and me. Okay? Okay, any other question? Okay, so please, I know your project B is not easy. It's a tough project, I believe. But you will learn a lot if you can understand the problem of the project B, and definitely you will learn programming skill, and the SQL, the syntax itself is not very the critical, but the more important thing is whether or not you can understand. Okay, such a query optimizer, indexing structure, data structure, and finally, so you can understand how your query is processed in the database. Okay, see you next week.